Good morning, students. Today we go to the next chapter, and I think it's the last chapter of your syllabus. The next chapter is difference amplifier. Now, to start with, we we try to understand what is a difference amplifier, right? Now, please have a look at this diagram, difference amplifier, and what we do, I'll show you the basic circuit. Mind it, a difference amplifier is not so simple. It is pretty complicated circuit for its required performance. But this is the basic thing. There is a power supply VCC plus 12 volt, 10 volt, whatever it is. This is a negative power supply. So first point you must take care of that this is a double-ended power supply circuit. It needs positive as well as a negative power supply. This is number 1 point. Number 2 point, you find there are left half and the right half. There are two identical circuits. Here we have shown only the input base resistor RB and collector resistor RC. Here also RC and RB. Although, as I said, actual practical difference amplifier will have many other components. Anyway, so this is one input where there is an input V1, and this is another input where there is an input V2, right? And they have obviously separate collector current because collectors are separate, but their emitter circuit is combined. That makes a major difference. This resistor RE works as an emitter resistor for transistor T1, also the emitter resistor for transistor T2. Let us consider the voltage drop across RE is VE, as shown here. The emitter current is IE1, emitter current here in transistor T2 is IE2, and practically IC2 and IE2 are same, IC1 and IE1 are same, and IC or IE is beta times IB, the base current which flows. Now, where is the output terminal? There is one output terminal from the collector of transistor T1. There is another output terminal from transistor of collector T2. And the output is the difference of these two outputs. That means if you connect a voltmeter between these 2 points. Normally, in all other amplifiers, the output is across the ground point. That means you connect a voltmeter across the output and the ground point. But here, you connect the voltmeter across the 2 output terminals. By the way, this kind of output is called floating output, and the other kind of output is called grounded output. So this is the basic structure of a difference amplifier. Next, as I said, the 2 halves are identical, left half and right half are identical. Mind it, I should give a caution here. If you want to make a difference amplifier in your laboratory with 2 different transistors, you will not be very successful because there are no 2 transistors in this world which are 100% identical. There is always a difference. In fact, this difference amplifier is actually a basic part of our integrated circuit where it is possible to create the 2 transistors identical. Anyway, 2 halves are identical. Next is output is VO1 minus VO2. So this is the output. And this is V2 and this is V1, the 2 different inputs. And there is a nomenclature. The difference mode input, VD, is input V2 minus input V1, V2 minus V1. This is a legend, you can say. V2, input V2 minus input V1, we call it a difference mode input. Say this is 4 volt, this is 3 volt. Then difference mode input is 3 minus 4 minus 3 equal to 1 volt. And common mode input, another terminology, is the average of the two inputs. Say this is 4 volt and this is 3 volt. Then 4 plus 3, 7 by 2 is equal to 3.5. The common mode input is said to be 3.5. These are the two definitions you can say. If you agree to these definitions, then from these two you find that if you multiply 2VA, or you can say VD by 2, from here you can find V1 is equal to VA minus VD by 2, and V2 is equal to VA plus VD by 2. So these are the three basic equations, derived equations, which you need to understand the performance of this difference amplifier. Next, we go for small signal analysis. Here we want to find out what is the gain of this amplifier and all that. This is there in your syllabus, which says that calculation of the common mode rejection ratio, etc. Though you don't need that calculation very often in your practical life, but since it is there in your syllabus, let's discuss it. And I have made the discussion as short and as simple as possible. I mean, there can be lengthy lectures on this small signal analysis, but I have kept it shortest possible. First point, considering the input of transistor T1, this is the input. What we find, V1 is equal to RB. Now this emitter current IE, when it is reflected to IB, emitter base side, then you know this resistor RB will become RB by beta, because current is beta times less. So V1 is equal to IE1 into RB by beta plus VE. So this is the circuit. So if you apply Kirchhoff's voltage law here, this is the equation. But here I have ignored a few things, two things. One is there is a base emitter voltage, VBE. Also, there is a base emitter resistor, HIE. But these base emitter voltage and base emitter resistance values are very, very small. And also, since the circuit is symmetric from the left-hand side and right-hand side, so ultimately they will get cancelled out. So to make it very simple for you, I have left them out. So this is V1. Now apply Kirchhoff's voltage law to transistor T2. What do you find? V2 is equal to IE2 RB by beta plus VE. So these Kirchhoff's voltage laws are fine. Then what is VE? VE is equal to IE1 plus IE2 into RE, because both emitter currents are flowing through RE. So this is the value of VE, right? So this VE should be replaced by this value. Now, V1 is equal to this, right? Now, here we have found V1 is equal to VA minus VD by 2. So VA minus VD by 2 is equal to IE1 RB by beta plus VE is IE1 plus IE2 RE. Similarly, for the transistor T2, V2 is VA plus VD by 2, VA plus VD by 2. Once again, IE2 RB by beta plus IE1 plus IE2 RE. So you will find there are two distinct equations and they are very similar to each other, right? Very similar to each other. And in fact, there is a mistake here. It should be IE2 here, because this equation is IE2. I do not want to stop it and correct it now. Let us consider it IE. Now, on the left-hand side is VA minus VD by 2 and VA plus VD by 2. If you look at the left-hand side, what appears to you? Appears there are two inputs. One input VA and another input minus VD by 2. And for transistor T2, once again, there are two inputs, same two inputs, but they are added. So if we consider this is one input and this is another input, then you can use superposition theorem. These equations can be solved by first considering VD equal to 0 and then considering VA equal to 0. That means you consider VD equal to 0, then this is 0, this is 0. You are left with only VA. And next you consider VA equal to 0. So you are left with VD and minus VD and plus VD. And then if you add the results together, you will automatically find the equations which you can easily solve by using superposition theorem. So we come to the superposition theorem. The same equations I have repeated once again. VA minus VD by 2 equal to this and VA plus VD by 2 equal to this. And also I have repeated here V1 equal to VA minus VD by 2 and V2 is equal to VA plus VD by 2. Right? So that you don't have to always go back to the earlier slide. So from here we start. We said we are going to use superposition theorem. So first we consider VD equal to 0. So here this is 0. Here also this is 0. If we consider VD equal to 0, then what you find, both inputs become same. The input here is also VA, input here is also VA. So both emitter current will be same. So IE1 will be equal to IE2 and I give it a name IA. Because left-hand side I will have only VA. So collector emitter current, I give it a name IA. If I do that, then look at this equation. VA is equal to, because VD is equal to 0, is IE1 is equal to IA, RB by beta plus this is 2IA into RE. From here I get IA is equal to, if you take IA common between here, IA is equal to VA divided by 2RE plus RB by beta. So this is IA. Now remember what is IA? IA is the both emitter current when VD by 2 part of the input is missing. When VD by 2 part of the input is not there, then IA is the both emitter current and we find its values here. Next we shall do, we have considered VD equal to 0. Now we shall consider VA equal to 0. If we consider VA equal to 0, then V1 is equal to minus VD by 2 and V2 is equal to plus VD by 2. And from there what we find, it is actually V2 is equal to minus V1. That means input here is equal to opposite of or reverse of input here. V2 is equal to minus V1. If V2 is equal to minus V1, then obviously IE2 also will be equal to minus IE1 because it is a symmetric circuit. And we give it a name ID, differential, right? Also, what is V, value of V then? Value of V then equal to 0 because both currents are flowing in the same direction as per the direction shown here, but one current is opposite to the other current. So the net current through RE is equal to 0, therefore V is equal to 0. Fine. If that is so, then we go to this equation. VA is equal to 0, so we are left with minus VD by 2. And IE1 plus IE2 is equal to 0 because one is opposite to the other. So what we are left with, IE1 RB by beta. Now this IE1, we have considered it, give it a name ID. So minus ID RB by beta. So ID is equal to, now this negative sign gets cancelled, is VD by 2 divided by RB upon beta. So we get two values. IA is the emitter current, equal emitter current when VD equal to 0, and ID is the equal and opposite emitter current when VA equal to 0. That means we have found two different relations for this to solve this equation. And obviously, then the current, then we can use superposition theorem. V1 is equal to VA minus VD2, VD by 2. Now we have considered current is IA when ID equal VD equal to 0, and current is ID when VD equal to VA equal to 0. So obviously, if V1 is equal to this and V2 is equal to this, then obviously IE1, that means this actual current, superposed current, is IA minus ID, and IE2 is IA plus ID. That means we have to do plus minus of these two figures. When you do this, so what is IE1? IE1 is equal to IA minus ID. That means this current VA divided by this minus ID is this. And what is IE2 is addition of them. So this plus this. So we get values of IE1 and IE2. Mind it, the equation is very symmetric, only there is a difference of negative sign and a plus sign here, right? So this is the IE1 and IE2. You can go back. This is IE1 and IE2. These two are repeated here for your convenience. Now, this is, we have analyzed the input side, that means base emitter loop. Now we go to collector emitter loop. You please remember from your basic circuit, basic cone emitter amplifier circuit, the voltage here is equal to VCC minus RC-IC, where this IC that I am calling is AC plus DC current, quiescent current plus signal current. If we discard the idea of quiescent current, only signal we are talking about, then is equal to minus RC and IC1, right? Minus RC IC1, and VO2 is equal to minus RC IC2. Now, IE1 and IE2 we know. And if we consider that emitter current is equal to collector current for the sake of simplicity, then we know VO1 and VO2. So VO1 is equal to IC1 multiplied by RC. So this becomes this VD part. There is a negative sign here. So negative, so this will become plus and this will become minus. So this becomes RC by 2 multiplied by VD, RC by 2 multiplied by VD, whole divided by RB by beta. And there is a minus sign here, minus, this becomes RC, this becomes RC divided by 2RE plus RB by beta into this VA is here. Similarly, VO2 is the same equation, only this part becomes negative. So we know VO1 and VO2. So, and what is the difference amplifier output? Difference amplifier output is VO1 minus VO2. So what is VO1 minus VO2? This part gets cancelled. We are only left with RC by 2. It will be replaced by only RC. RC divided by RB upon beta into VD. So mind it, what do we discover? That the output voltage of the difference amplifier, when output is taken between the two collectors, depends upon the difference mode voltage only. That means V1, that means only upon V2 minus V1. That is the most important thing. The output does not depend upon anything of their common mode voltage, that means VA plus V2 plus V1. Output depends only upon the difference mode voltage, which is VD, right? Now, this above relations, VO1 and VO2. See, this is a factor, this factor is repeated here, and this factor is repeated here. So if we give this factor a name of AD, so it becomes ADVD minus, if we give it a name AA, then AAVA. And VO2 becomes minus ADVD minus AAVA. Now, you may ask that why suddenly we take this decision. If you look at this equation, it shows you that VO1 is some multiplication factor multiplied by the difference voltage minus another multiplication factor multiplied by the additive voltage, right? VA. And VO2 is the same multiplication factor AD with the negative sign into difference voltage and minus AAV. This AD and AA, AD is equal to RC upon 2 by RB by beta. This is called difference mode gain because this is the difference voltage VD multiplication factor. And this is common mode VA multiplication factor. So AA, this factor is called the common mode gain. It shows that the output is actually some difference mode gain multiplied by the difference voltage and difference mode gain multiplied by the difference voltage plus minus the common mode gain multiplied by the common mode voltage, right? So this is the value of differential mode gain, and this is the value of common mode gain. I do not know whether you will at all ever face these questions in the examinations, but if you need in future, what is the difference mode gain of this difference amplifier and what is the common mode gain of this difference amplifier? These are the two things, right? Now, mind it, this is basically a difference amplifier. That means the output should be a proportional multiplication or amplification of the difference mode, of the difference voltage. That was VD. This factor, which appears out of the common mode voltage, we do not want it there. We want it to be zero, right? So here also, we want only the difference mode part. We do not want the common mode part. So actually what we want to design an amplifier such a way that this common mode gain is as small as possible and difference mode gain is as large as possible. So that if you give 2-volt input and also 2-volt input here, the output should be exactly zero. If the common mode gain is zero, then output will be exactly zero. Or it should be very, very small, few microvolt or nanovolt. And we want the difference mode gain should be very high, so that if it is 3 volt and it is 2 volt, then 3 minus 2, 1. That 1 should be multiplied many times with amplification factor AD, which appears at the output. That is the idea and purpose of a difference amplifier. Difference amplifier is purpose is to amplify the difference input. But unfortunately, this circuit, this output also contains a part of the common mode input. Now, there is a figure of merit where figure of merit is called common mode rejection ratio. This is a figure of merit. It is a ratio of difference mode gain by common mode gain. We want difference mode gain to be very, very high, common mode gain should be very, very low. So we want this should be very, very high value. And AD, when we put a values of AD and AA, this is equal to this figure. This depends upon the emitter resistor and base resistor and beta of the two transistors. But normally, 2RE is much, much more than RB of beta. So this factor, if we cancel out, then 2 and 2 gets cancelled. So this becomes beta RE by RB. So to have a very high common mode rejection ratio, emitter resistor should be high, beta of the transistor should be high, and base resistor RB should be low, right? This is what is common mode rejection ratio. I repeat, common mode rejection ratio is the ratio of difference mode gain upon common mode gain. And it should be as high as possible. And just to give you an idea, for very common IC 741, which is a difference amplifier integrated circuit, for IC 741, common mode rejection ratio is almost 10 to the power 10. So practically it is infinite. There is another term in your syllabus. There could be many, many terms, but this term is in your syllabus. ICMR. ICMR is common mode input voltage range. That means input common mode range. Right? If we go to earlier circuit, we go to this circuit, this input here and input here. Right? Now, what can be the maximum input here? What can be the maximum input here? So that the performance of the difference amplifier is not degraded much. Right? And our basic knowledge of this circuit shows that this input range here should not be more than VCC or less than minus VE. That means not beyond plus minus 12 volt. Right? If you are designing or assembling a discrete amplifier like this in your laboratory with plus minus 12 volt, you will find the maximum input range is something like maybe 10 volt or so. But the integrated circuits that we use nowadays, this ICMR value is just slightly less than VCC. If you connect the op-amp to plus minus 10 volt, then maybe you can apply an input up to plus minus 9 volt without any degradation. But what is the range? It is given in the data manual of the IC that you are using. So this is a difference amplifier. Basic idea of the difference amplifier. In our next lesson, we shall see the integrated circuit difference amplifiers. This we shall see next day. And this integrated circuit difference amplifiers are normally called as operational amplifiers. Because you know why? And abbreviation is op-amp. Why? Because sometime in 1960s, in between 65 or so, when operational amplifier was first designed and put into use, then it was found that all the various functions, amplification, negative amplification, integration, differentiation, and all various kind of analog circuitry for which people used to break their head to design the analog circuits with transistors or FETs. It was suddenly found that this operational amplifiers, which has almost infinite difference mode gain and almost zero common mode gain, can be very easily used for all these operations, all these applications, very easy. That we shall see next day. How easy to make an oscillator, how easy to make a timer circuit, how easy to make a differentiation circuit or integration circuit, how easy to with this op amp. So that is why since it is used for all kind of operations, since then it was called operational amplifier. Otherwise, there is no other need for this name. It is just a difference amplifier, but the integrated circuit is called op amp. So we stop it here today. Next day we shall go into the op amp. Okay.